Welcome to part 10 of my series on foundations of arithmetic, algebra, and graphing. And it's video number 10. It's part 2 of a sub-series called division of integers, meaning and application. In the last video, video number 9, looked at a couple examples. Here was one of them. You have 5 people in your family. You go to pick 147 apples. How do you split them fairly? And how many apples are left over? The answer ultimately was 147 divided by 5 gives you 29 for the quotient, meaning each of the 5 people get 29 apples. And the remainder is 2. That means there were 2 left over. Thought about that with the simpler problem so that I could draw a picture. Initially, I imagined my apples lined up in a row here with 15 apples and 4 people. And I split up the apples by essentially counting off 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and seeing that I couldn't continue because I have 3 left over. I want to illustrate that there's another way to think about that. You can imagine each of the 4 people being in a row, and they each get 3 apples. These apples are grouped together. I'm circling apples by which person gets them. Person 1 getting those 3 apples, person 2 getting these 3, person 3 getting these 3, and person 4 getting these 3. That's 12 apples total. There are 3 left over. That's another way to visualize the fact that 15 divided by 4 is 3. 3 apples are circled here, and there are 3 left over. That picture is actually also illustrating, if I imagine circling this one, if I imagine there's 5 people instead of 4 people, that 15 divided by 5 is 3. If you've got 5 people and 15 apples, each person would get 3 apples and there would be none left over. In this case, 5 goes evenly into 15, you might say. Quotient is 3, the remainder is 0. I could put an R0 here. There's none left over. 3 is a factor of 15. 5 is a factor of 15. I can say 15 divided by 5 is 3. I can also say 15 divided by 3 is 5. I can interchange with the remainder of 0. I can interchange the role of 3 and 5 in that case. And so these would be examples where when you do the division of 2 integers, you get another integer. That didn't happen up here. 15 divided by 4 was not 3. It was 3 remainder 3, or if you plug it in your calculator and look at the decimals, you'll actually see it can be represented as 3.75. Not an integer. The integers are not closed with respect to the operation of division, whereas they were closed with respect to the operations of addition, subtraction, and multiplication. They are not closed with respect to division, excuse me. Another thing to note about division is that division is not commutative. Even though 5 goes evenly into 15, and the answer is 3, which is an integer, but that's just lucky in a sense. If I switch the roles of the 5 and 15 around, I do not get an integer. 5 divided by 15 is not an integer. What is it? Well, again, if you do it on your calculator, you'll see a 0.3 repeating. In terms of quotient and remainder, you could write it as 0. Remainder, let's see what I'm trying to say here, 0 remainder 5. 15 goes into 5 0 times with a remainder of 5. 5 can be thought of as 15 times 0 plus 5. Kind of a weird thing to do, but it is still true. 0 is not what 15 divided by 5 divided by 15 is. You'll see again in your calculator 0.3 repeating. These are not equal. It's supposed to be a not equal there, illustrating that division is not commutative. It does not satisfy the commutative property. I think the only other thing I really want to emphasize in this video is a little bit more about factoring, and hint you to some things about prime numbers. Anytime you have an integer, let's just say we pick 140 maybe. Turns out to be useful in many situations to try to factor that number. figure out some numbers that go evenly into it, and especially you want to focus on what's called the prime factorization. 140, for example, is 2 times 70. And if I write the 2 and the 70 down like this, and I'm making a tree diagram here, that's going to help me continue the process to ultimately find all the prime numbers that factor into 140. Now, maybe you recall what a prime number is and maybe you don't. I'll explain it as I go here. 70 is 2 times 35. 35 is 5 times 7. And 2, 2, 5, and 7, those are all prime numbers. Prime numbers are numbers whose only positive integer divisors that divide evenly into those numbers are 1 and the number itself. So it turns out the list of primes starts like this. Notice that 2 is a prime, only 1 and 2 divide evenly into 2. 3 is a prime, only 1 and 3 do. All the other ones are odd numbers. Some odd numbers are skipped, like 9. 9 is not prime because it's 3 times 3. 15 is skipped because it's 3 times 5, etc. Turns out any number can be written uniquely as a product of primes. And in this case, the prime factorization of 140 is 2 times 2 times 5 times 7. This factorization tree helps us see it. That's unique up to switching around the order of the factors. Wanted to mention that as just a basic fact to know about numbers. It's maybe not going to be important for most of the problems you end up doing in math. But I also wanted to just inspire you that primes actually have some importance for real life. If you look up RSA codes, that's a famous example of a security system, an encryption system for encoding information secretly. So, for example, your transactions on the internet are secure. It's not the only kind of system. RSA is a particular kind of system for encoding secret codes. But it's a very famous one, perhaps the most famous one. And it again helps keep your internet transactions secure. When you put your credit card number out there, you can be confident that nobody's going to be able to break it once it's encrypted. Anyway, the only thing I want to mention about this is that RSA codes, your security on the internet, is based on prime factorizations of all things. So prime factorizations, especially at really, really big numbers, unimaginably big numbers, turns out to be important, vitally important for our real world.